Mm, I think, yeah, we are recording. Fine. Okay. Welcome to the lecture 9 of of this course, I think, um, of generative modeling using generative modeling. VAs we already covered, and just as a recap of what we did last class was that we looked at we spoke about GANs a while back, and then we gave some idea on what FGANs are, and we saw mainly two outcomes of this whole idea. One was that why this comes as a generative adversarial sort of a formulation that comes out. That is basically that there is one network which is trying to maximize a particular quantity, whereas the other network is trying to minimize the same quantity. So hence we're looking for a saddle point sort of a formulation when you look at the whole parameter space. That was one thing that came out of this. And second thing was that there is this an idea that we have to train one network more than the other, and that was basically when we were trying to find the value for this f divergence so when you maximize the t opt function, then you get a good estimate of this f divergence, and therefore then minimizing this f divergence would make sense. Hence we looked at this sort of formulation. I also spoke about Wasserstein GAN a bit, but we'll come back to it if time remains. I'm just still figuring out how to motivate the example and come to it. And we spoke about things like mode collapse and some interesting GANs, like for example, cycle GAN and bi-GANs. And we spoke about how this relates to the info VE concept, where the authors mentioned that we can just look at optimize the last term of this objective function using a adversarial learning, and we saw the whole network example here. So today we'll move to this idea of diffusion models, and as the name suggests, we'll first briefly talk about what diffusion is, and how how this could be like a motivation to look for solutions in ML, right? Um, okay, one second. Yeah. Okay. There's some issue. One second. Just a moment. Yeah, good, fine. Okay. Um, comes here. Okay. So let's think about this diffusion as a physics process, right? For let's say, for example, I have a bucket of water and I'm dropping an ink, one drop of ink in it. So what ends up happening is over time, the ink starts diffusing throughout the water solution, and we at the end we get something like a water plus ink solution, right? And in a sense, this is something like an isotropic sort of a diffusion process. So where at the end, any direction that you look at in this particular solution, you get similar sort of a view. So we could think of this particular process as going from something that is structured to something that is unstructured, right? And I'm saying structured because I can basically define the state of this particular ink and water, this one, as let's say one variable, that is, for example, let's say the position of the ink droplet, right? So I can use one variable to define what this state will be, whereas here there's nothing, I think too defined in that sense, right? It's just that the solution is now homogeneous. There's nothing to define in this case. So possibly, if we could reverse this process, right? That is, try to understand, how this particular, which particular, position of dropping the ink could give us this sort of could give us this sort of unstructured solution, may help us come back to what happened in the beginning. Now, so one thing possibly is that if this was allowed to go up to infinite time, then it is impossible to come back. But if you're able to stop it somewhere, right, some point in the throughout this process, then possibly we could try to backtrack this whole system. So uh,
in some structure, that's why we are able to reverse it.
correct. So let's say it is that if it is t infinity, if it is there, then it is unstructured. But yes, if t is less than infinity, some value of t less than infinity, then we could call it some sort of structure is there, and we could probably come back from there to the actual one, right? Um, so we'll now look at the formulation with this particular system, and one second. I guess we are back online. Okay, fine. So yeah, so okay, so we'll start the diffusion model formulation today. Now consider, so we have been looking at x as a random variable for data. So let's take x naught, x0 as a random variable for data, and as again obvious that we don't know p of x naught, we don't know its probability distribution as usual, but we have samples from p of x naught, right? And our goal is still the same. We want to generate samples which look like the samples that we have. So now let's say I define a random process in this way. That is, let's say xt is defined as some root of alpha t into xt minus 1 plus root of 1 minus alpha t into some epsilon, where epsilon is drawn from a Gaussian distribution, right? Now again, from the face of it, what does it look like the values of alpha t could be? Any thoughts?
Between 0 and 1.
Between 0 and 1, right? Just very simple, right? So between 0 and 1. And for now, we'll not argue about the closeness or not. We'll see that later, right? Okay, so if this is the case, what is the distribution of xt given xt minus 1?
No, this is Q.
Okay, yeah. So I'm defining the conditional distribution of the new random variable that I've got in the process with respect to the previous condition on the previous random variable. I'll call it Q. Gaussian only. Centered on, yeah.
This xt minus 1.
Just xt minus 1?
Lambda times square root of lambda times alpha t.
Square root of alpha t?
Yeah.
Xt minus 1?
Yeah.
Right? And what's the variance?
1 minus alpha.
1 minus alpha t I, right?
Yeah.
This is the distribution of Q, right? And this we know from the again the same the linear transformation theorem that we have done before, right? Okay, so now can we, so basically we can see this as a Markovian process, right? Because each process in this x1 to xt depends only on the previous term, not on the history. Given the previous term, it's independent of the remaining history, right? So therefore, we can see it as a Gaussian Markov chain with a Gaussian conditional process, right? So if you think about it, what is the joint distribution of all these variables given x? How could we write something like this?
So Q of xt given x1, then Q of x3 given x2, and so on.
Xt given x1, is it?
So basically, like multiplication of like Q of xt given xt minus 1.
Xt minus 1.
And product of that.
Product of this, right? Correct. So t, let's say t1 to, I'm using t here. Right? So let's say some I equal to 1 to t. I can write this as q of xi given xi minus 1, right? Again, that's because of Markov chain, property. So, no, right? Because the last term will take care of it. Because the last term will become q of x1 given x0. And therefore, I need not write anything because I'm asking the conditional joint distribution, right? Conditional joint distribution of this. Okay. So now, can we represent xt in terms of x naught directly though?
Yeah.
Right?
Because all of these terms are known to us.
Are known to us, right? So basically, I can use this to do a simple recursion and get back x naught, right? Go to xt, go to x naught from xt. So let's do that and see how the form comes out. Yeah. So let's say xt was root alpha t xt minus 1 plus 1 minus root alpha t epsilon, right? Now I can write as root alpha t into this. I can write it as root alpha t minus 1 xt minus 2 plus 1 minus alpha t minus 1 epsilon plus root 1 minus alpha t epsilon. Correct? And these epsilons are different actually, right? So just to make sure that it's captured, let's write it as alpha t, sigma t, and epsilon t minus 1, right? And where all epsilons, regardless of t, are sampled from this Gaussian distribution, right? So this becomes root alpha t minus 1 xt minus 2 plus root alpha t into 1 minus alpha t minus 1 epsilon t minus 1 plus root 1 minus alpha t epsilon t, right? So now, can we simplify this further? If you think about it, both of these are Gaussian distributions, right? So, can we simplify these two? That's the question.
Yes, because
right?
both are same mean,
Same mean, yes.
same variance, so we can.
But yes, but what are we adding? So the variances are a bit different. Okay, so we'll take so I'll just mention a result here and then we'll just go ahead with that. So let's say if I have two Gaussian distributions, let's say X is some Gaussian distribution, let's say with mean mu, variance, let's say sigma X, right? And then your Y is another, Gaussian distribution. And the fact that if they are independent, right, X is independent of Y, then the sum of these two Gaussian distributed random variables can be seen as just the mean of, add the means and add the variances also, right? I think again, adding means is coming from straight from, usual probability distribution. Variance also is usual, but the fact is it's again a Gaussian distribution. That is important for us, right? So now, if you think about it, this root of alpha t into 1 minus alpha t minus 1 epsilon t minus 1 is a Gaussian distribution with mean 0 and variance is alpha t into 1 minus alpha t minus 1 I, right? And root 1 minus alpha t epsilon t is again a Gaussian distribution with mean 0 but 1 minus alpha t I, right? So their sum basically is going to be mean 0, right? And variance will be addition of these two. So alpha t minus alpha t into alpha t minus 1 plus 1 minus alpha t, right? Whole into I. So you can cancel out these two. I get 1 minus alpha t minus 1 I, right? So therefore, I can now write this xt as root alpha t minus 1 xt minus 2 plus, so now I can write this whole thing as root of same, right? 1 minus alpha t minus 1 into some epsilon, right? Let's say t tilde or whatever. Again, this is again sample from a Gaussian distribution, right? Very simple. So therefore, now we have come to, so this is xt. So if we continue like this, what will end up happening is, as you can see, we just going to multiply until we get to this particular value, right? So I can just write this as alpha t minus 1 until let's say alpha 1 or whatever, right? Into x0 plus same 1 minus alpha t minus 1 until alpha 1 with some Gaussian distribution, right? So this epsilon is again a Gaussian distribution, right? So basically we added the variances here. The variances basically turned out to be subtracting these two. I mean, these two will get cancelled. So I get the final variance comes out to be 1 minus alpha t into alpha t minus 1 into I, right? And that can then be seen as this is the mean from previous. So, and these two random variables get added up into this particular random variable, right? So, and where this again got from a Gaussian distribution. So if we continue this process, we'll get something like this, right? So now, therefore, I can get the qt xt distribution conditioned on x naught directly, right? So it's basically a Gaussian distribution for xt centered around this distribution, this mean, right? Alpha t bar, where alpha t bar I've given it as like this, right? Into x naught, same 1 minus alpha t bar I, right? That is the form for this particular distribution, conditioned on x naught. Mm.
So if T is very large.
If T is very large.
So like, doesn't depend on x.
Correct. That's exactly where they're coming to. So as T tends to infinity, what will happen to Qt of Q of xt given x naught, right? Because it'll go to 0, right? Because as we know, all alpha t's are in this range, 0 to 1 range, right? So their product, infinite amount of products will tend to let's say 0. So therefore this will become n of, so this distribution will tend to the distribution which is xt, but 0 mean and unit variance, right? And then what can I tell about q of xt? This is conditional distribution of xt given x naught. So what is q of xt then?
Gaussian.
Again Gaussian, right? So how do you argue that mathematically though?
Because 1 minus alpha bar t will go to 0.
Right.
Therefore, like, will go to 1.
Will go to 1.
And therefore, like, it's from that equation, it's like unit variance and 0 mean.
No, this is fine.
Property of Gaussian. That base conditional formula.
Conditional formula.
There is a mathematical property of Gaussian. Like if the condition is conditional distribution is Gaussian, then the is also Gaussian. Yes.
Right. Yes. So basically, if you want to write it in a different form, I can basically say that it's nothing but the integral over this quantity, right? Over x naught. Now this I can, as you said, conditional. So xt given x naught into, let's say, q of x naught dx naught. We're not defining what q of x naught is, but that's okay. That's it. Yeah. So this is Gaussian. Doesn't depend on anything on the x naught. Integral q of x naught is always going to be 1, right? This will be 1. So therefore this also becomes n of 0i, right? So now what have we shown? We have gone from this x naught, which was data, right? Something structured in this x naught space, and let's say we are going to x infinity, right? Because we are talking about as t tends to infinity, and we've gone to something like an isotropic Gaussian. Isotropic Gaussian in the sense it's if I look at any dimension, it's the same shape, nothing different between two dimensions. So this is basically going from structured to this unstructured sort of a distribution sort of thing. So this process is called the diffusion process or the forward process, right? So we have data, and we are going from this data to complete basically just noise, right? Pure noise. And again, this is very intuitive, because what we're doing is we're keeping on adding small amount of noise every time. So any structure in this data will be lost. At the end of the day, we will have what we'll have is only noise, right? So this is the forward process. This is what we call as forward process. Now, the idea is, so now let's say if we could somehow figure out the reverse process with whatever, mathematical jugglery or whatever. So then the way that you could sample or get new data would be basically start from this, right, x infinity, because we know we can sample from isotropic Gaussian, and if we have the reverse process, keep on following this reverse process and get samples from x naught. That is the idea in this whole diffusion system, right? So the bigger chunk, I mean, the chunk of the matter lies in trying to figure out how to get this reverse process out, right? So now for that.
So do we really start from x infinity?
No, that's where things will become a bit clearer. I mean, yeah.
So from where do we start?
Huh.
See, because we don't need x infinity. We already know what x infinity is.
Correct. But we know, but we need x infinity to take those steps back and come to x naught. So basically,
but we don't need to compute x infinity.
We don't need to compute x infinity. Correct. Yes, that is true.
So we are okay. Understood. So we just want to find the backward path. And we know from where to start that backward path.
We know where to start backwards. Correct. Okay. So we know where to start and we know where to end also, by the way. It has to be a sample from the real distribution.
It has to be similar to the sample.
Distribution, right? So at the end, whatever algorithm that we want to learn should basically start from this isotropic Gaussian, right? And end at and then give me a sample from this distribution.
Right.
And the way I can train this is because I have these endpoints also with me. So I know starting point, I know the ending point. What I need to figure out is this process to go back, the path to go back.
So now for different probability distributions, for example, like distribution of dog images,
right?
Distribution of cat images,
right?
The backward path will differ.
Will differ, correct.
The starting point will be same.
Yes.
Ending point will be different.
Will be different. Okay.
X infinity for the dog.
Huh.
Okay. And the cat should not be same. Otherwise, what's the point of using neural network to it will map to same thing, right?
It will not, because you cannot really get infinity in usual this one. Some t is where you will stop.
Okay.
Right? And now you will assume that xt to have unit isotropic Gaussian. And from there now you will take a backward.
There's some representation in that back latent space whatever. And then we are going back to
the data space.
Your starting point is same.
Starting point is same.
Then you will map to same x0, right?
See, starting point is same, but the paths are different. Therefore, depending on which data it has been trained.
Paths are different.
So let's say if you have, let's say, a set of cat images and set of dog images.
So you separate train them.
Separate training that, yeah, we're talking about separate training that. And even if with training that together also, the idea, so then the question that we're asking to the network is, give me a sample either from dog or cat. So then, yeah, different.
Sample from N0,
yes.
And then
use the backward process to come to the data space. That is the point.
But it's okay to not have any trace of the data at x equal to t, where t is larger.
Yes, it's okay not to have.
So, for example, like if we start adding noise to cat data, noise. So we need not like, and we go to some uniform Gaussian distribution.
Right.
And if we do the same thing for like dog image, we will go to the same distribution. So my question was should that distribution ultimately have some information from where it started? And you see, like it's not necessary.
It's not necessary. At least the power process doesn't say anything about that. X infinity will not have anything about the data. For any data points you give it, it will come back to Gaussian. That's the idea.
Maybe it's also N0, right? Cats
also N0, and this is exactly what we showed here. This is exactly the whole point. It doesn't depend on X naught. So for any X naught, it will go there.
So dogs and cat simultaneously trained. Sorry, dogs and cat simultaneously trained will end to N0, right?
Correct.
But the essence is
steps you take will be different.
Yeah. So basically, this one point I'm not able to get.
Okay.
Basically, diffusion is happening. Okay, and so then like in that N0 space there is like particular space. Like this is tolerance. Otherwise, not possible.
No. At least the forward process doesn't tell you anything about that. So in forward process, you have at the end at t infinity, you have lost all information about the data. You don't know where that cat image came to, from to a cat image and a dog image. At the end, at t infinity, will get mapped to some point in this space.
How is it able to then become?
We'll come to that. We'll come to that because hence the whole point here about the reverse process. So the biggest point was if we're able to figure out a reverse process, we'll be able to do that. That's the biggest point, right? And it's also the reason why I mentioned this idea. We cannot do t equal to infinity in practice. So we have to choose something, and that's where this idea comes in, which is the something which was given in 1949. Some paper some guy proved about this, this Markov chains system. So let's say if I have a forward process, which is a Markov chain, in which this noise that is added is small enough. Okay, if it is small enough, then the reverse process will have the same functional form. Okay, so what that means is, so in our reverse process, we have from x capital T to x naught, and it will be a finite chain. We cannot do it as a for infinite chain. We don't start from x infinity. So now the point I'm saying is that this will have the similar functional form. What does it mean? It means that x capital T will be n0i. Okay. X0 to t, that is all these, the joint distribution of all these random variables will be of this form, where it's a Markov chain sort of a thing, right? Because we saw the forward process was also Markov chain. It depends only on the previous step. Here in this case, the previous step is in forward in time, right? So therefore xt minus 1 given xt, that is the forward the Markov chain here, and you start from p of xt. And also another point is that these, because we said that the forward Markov chain steps are all Gaussian distributions, the backward the reverse distributions will also be Gaussian distributions, right? With some mean and some variance. Okay, so as you can see, so this is exactly what it means when you say same functional form, right? So this is the Markov chain idea. This is the Gaussian idea, and this is the idea of the the t equal to infinity case in our scenario, right? Now, so one formulation that the authors have explored and everything. What they've said is they keep this sigma of xt comma t as a assumed to be some sort of a sigma t squared I. And we'll look at we will see how to compute this in closed form. We'll actually get a closed form solution for this. What should be the ideal sigma squared t? They've also tried to learn this and everything, but they came to this solution which worked for them. So we'll just use that and move ahead. So now, okay, one thing that I forgot to, as you mentioned. So, okay, so what is the size of the data that we are currently assuming? We assume it to be some R power D space, right? Now, what is x1, x2, x3, and all of these, dimensions? Same, yeah. Right? All of these are same dimensions. So this whole process is happening in the RD space only, right? So all of these belong to this RD space, right? And it's a process in the RD space. So if you think about it, what should this function map to? Right? This function is taking an RD element and giving back an element in RD again, right? So this function basically takes xt and t and gives back some mean of this distribution. So because it's a function, we can use what? Neural network. That's it, right? The recurring theme of this whole system, right? So we can use NN as a function approximator. This is where this networks will come in, right? And now we will so if it's a function approximator, using neural network. So basically, sorry, yeah, go ahead.
T, we are borrowing the T, right? It's dependent on T.
Yeah. We'll have to take, yeah, sorry, yeah, it'll take a function, it'll map RD plus 1 space into this RD space. Yeah. So see, because the point is, again, here
for every input.
Yeah, correct. That is a good point in our case, right? Why? Otherwise, I would have to build multiple different neural networks for each time point separately. Rather, what we have done, we have taken a more like a sort of restricted sort of space here. We're saying we'll use the same function, we'll use the same network, give time as the input. Give time as the input, right? So this basically maps your RD plus 1 space into an RD space, one network that we have, right? And so therefore, I can write this as mu theta, parameters of the network, and all of this now becomes p theta. Right? And again, this is a number theta anyway, so but that's the idea, right? This is all p theta. I'm writing it as. So basically, this is our model distribution, right? So p of x naught is the true distribution of the data unknown to us, P theta of x naught is the model distribution. Right?
So, just one question there.
Yeah.
Why do we ultimately we want to generate that one particular image x naught?
Correct.
So now why do we need to like give it time as input and say like for this time input generate something, next time input generate something, etc. etc. Rather than like training one neural network with d-dimensional input and d-dimensional output. That's all. Because like we did the maths and found out like it's a very simple solution which it should ideally be able to learn.
Right.
Distribution of xt.
Distribution
Distribution of xt.
Distribution of xt.
So that when we consider this t to be large enough, then only an x0i assumption is good enough.
That is true. I think what it's asking is why should you give t as input in the first place?
Exactly.
So
just to visualize it, etc.
No, so we'll see. We'll see the functional form that it comes to. We'll need that t as the input, and it will also become important while sampling, because we have not even discussed sampling till now. By the way, we'll see where those issues will come in. So that reason also we take t into as input.
So see, we at least in the forward problem, we get a very like straightforward solution that xt, x capital T, is equal to some Gaussian having some mean which is computable. Computable in the sense like closed loop form.
Right.
As well as some variance.
Stochastic differential. Stochastic differential. This is, what is this called? Stochastic.
Markov chain, not the end.
Markov chain, yeah.
But
not that equation. Complete equation. Xt equal to xt minus 1.
Correct. So ultimately, solution we know, like where mean is under root of alpha t minus 1, etc.
Right.
Variance also we know 1 minus. So ultimately, what we are essentially saying that if I know x naught, I can compute xt.
Correct.
In the forward process.
Yes. Right.
And same thing, we are exactly same thing we are saying that. So we don't need multiple functions for coming from xt to x0. One function would be enough. So we're asking like why are we giving time as input? We are actually that was my question.
Oh, but you're saying, okay, you're saying that I can have just a single function that takes from this to this, is it?
Yeah.
No, that will be a problem.
Okay.
Because see, so what has happened at the end is that we have added small amount of noise. That is true, but we need to now denoise the data. This straightforward denoising will be very difficult for the model to come back to.
Possible.
So what we'll do is we have to do it in steps. We have to go, okay, small noise, keep rooming, and then finally come to x naught.
But at least the closed loop solution says it's possible.
Yes, correct. Because now I can always write p of x naught. I can write as an integral over this, and get a nice solution and all of that. Practically very difficult. It will not be able to jump that one step. It has to do that small steps and go there.
Makes sense. It's very good question.
Mm-hmm.
Theoretically, it should.
Yeah, why not just learn a function directly from x naught text to this one? But the reasoning there was only because it has small noise. This was true, and therefore the reverse process should also should follow that property of small noise removal, incremental sort of a thing. Only then you'll be able to recover come to x naught easily.
So it's like this basically every time you see some context,
right?
Apply some method based on that.
Denoise.
Again, then you denoise. Again, see the context.
Correct. And then denoise. Yes.
Yeah.
Correct.
But applying the same method and applying is difficult.
Is difficult, right? That's all.
Like RNN, recurrent kind of computation.
In some sense, it will come to that.
We are using same network.
Same network, yes, that is true. Yes. So same thing will go back, and then you'll keep on doing that. That's how it will come.
So it's basically like you have a old portrait which is full of like dust. You're not able to see anything, but you can like judge what it is. So you like scratch something.
That's a very good example. Yeah.
Scenery is there. Then you scratch no. Scenery not on a beach side.
On a beach side though.
Like you like scratch.
Scratch somewhere and you see.
Yeah.
Nice, very good example. Yeah, that makes sense actually. Yeah.
got it from this thing, like incremental.
Incremental sort of thing, yes. Yeah.
The first step will only tell you, oh, it's some scenery, not like some bus conductor.
Correct. Yes.
It's some scenery, okay. So scenery where? In a forest, in a mountain, in a
right.
Beach side. The beach side, you go, it's ultimately a photo of someone surfing. So that is only incremental.
Correct. Yes. Very good example. Yes, correct. Right. So okay. So now we have come to this idea that okay. So now I have a so now our point is this. We come back to the same problem statement that we had before. So I have a true distribution. I have the model distribution, and we know one way to solve this problem. That is, we already saw in VAs. We can look at KL divergence, right? And KL divergence reduction.
What is here also? Increase the theta of x.
P theta of x naught, correct. Yes. So we want to reduce the KL between P of x naught and P theta of x naught. And again, as we discussed before, this is so minimizing this is equivalent to maximizing the log likelihood, right? Log P theta of x naught, right? Yeah. Under the expectation again, right? Under, yeah, correct. So under the true expectation, what a P of x naught samples will take and get this, right? So now we'll derive that here, and this is where the math gets interesting. So we'll do the same thing. So now, okay. So first of all, we had x naught x1 until x capital T, right? This is what we have in P theta of x naught. So how would we write this P theta of x naught in terms of this joint distribution? Right? Multiple, I mean, yeah. So sum of, I mean, right? So marginalizing over all these variables. So x1 to T, P theta of x naught to T, right? Sum of this one, dx1 to T, right? Now this can be written as log of, log of integral. Now here is where I will add and sorry, multiply and divide. Again, same sort of variational sort of approach. What we will do is we will look at Q of x1 to T given x naught as the variational distribution for this, right? So this I can write and do this, right? This is fine. Makes sense, right? And again, so last time, so we had issues with this previously. We spoke that this should be, have support everywhere and all of that. That is true again because all of this is just a multiple Gaussian distributions. So this will have support over all possible values in this space x1 to T. So we are fine with multiplying and dividing. No issues with that. This can be now be written as expectation over. Go ahead. Over Q x1 to T x naught, and what is the expectation of? What is the function here?
Yeah, theta of
P theta of divided by this, right?
Yeah.
So Q of x1 to T given x naught, right? Now again applying Jensen's inequality, this becomes a lower bound on x1 to T given x naught, log of P theta of x naught to T divided by Qx1 to T given x naught.
Can I ask,
yeah.
What was the support you're talking about?
Support is this one. See, I'm dividing by some number. That number can't be 0, right? So, but that is, so we are okay with that here also because of the fact that Q is a multiple Gaussian distribution. So nowhere it will be 0, exactly 0 at least, right? So again, this is the lower bound. So the idea remains same. You increase lower bound, you will increase the log likelihood, right? Your log likelihood will increase, right? Okay. So now let's consider this lower bound. We'll see how to get some terms out of this. So the lower bound will now consider this. I can write this as x1 to T given x naught log. Now P theta of x naught can be written in the joint distribution format, that is P of xt with multiplied with all the possibilities, right? So T equal to 1 to capital T, I guess. So P of x t minus 1 given x t. Is this right? Yeah, correct. Right. So start from capital T here So t minus everything, and then at the end we get p of x naught given x1, and that's how we want it, right? Again, divide by, this is the conditional joint distribution. This also we have a way to write it down. This I can write as t equal to 1 to capital T again, q of x t, x t given xt minus 1. Correct? This is all, nothing much here, right? Now, same expectation, log of, now we'll do some math jugglery. So what we'll do is, we will remove the qt terms here. Okay, so what we'll do, we'll write it as q of xt given xt minus 1, just the last term, right? And this remains a product from t equal to 1 to t minus 1, right? So q of xt given xt minus 1, right? And I will take the first term, that is p of x naught. So p of x naught given x1, I'll take it out and write this as from t equal to 2 to capital T. Correct? Because the first term went away, right? Now, again, same expectation of same quantity, log of. Now let's look at these terms separately. So q of xt given xt minus 1 is one term into p of x naught given x1 is one term into this. I can write it as t equal to 1 to t minus 1 xt given xt plus 1. Is this right?
Okay.
Right? Just changing the this one. So, sorry, p of xt given xt minus 1. Yeah. Right?
Yeah.
Fine. Okay. So now we'll separate these terms out. So log of, again, log of multiplication. So addition, and apply the this generative expectation. Now what will come out to be is three terms. Expectation over this quantity, by the way, just to not forget, p of x naught given x1, sorry, log, right? This term, right? Then plus expectation, same, log of p of xt given q of xt given xt minus 1, correct? Plus, this is multiplication, again, log, addition, all of that jugglery. So we'll get sigma t equal to 1 to t minus 1 log of p of xt given xt minus 1 divided by q. Oh, sorry. So this needs to be under the expectation, right? So, yeah, expectation of x1 to t given x naught, xt given xt minus 1. So this is plus 1 over here. Right? Okay, till now all clear? Fine. Now, let's think about the second term for now. If this was, let's say, I mean, we're trying to optimize this function, right? So are there any parameters in this which get affected? Are there any parameters in this particular function, in this particular term?
Parameters in the sense?
The parameters of theta, right? P theta we want to this one, right? So parameters of the neural network, right? So are there any parameters here? Is Gaussian. This is Gaussian, and this is also Gaussian, but again no parameters, right? So this term effectively we can just ignore while trying to optimize this thing, right? Okay.
So
Now,
here it's a Gaussian only if t tends to infinity.
but we have assumed p of xt to be Gaussian, no?
Yeah.
The forward process, so the reverse process is we start with p of xt is Gaussian. Now we'll take only these t steps to come back. That's the idea, right? Okay. So this is nothing to optimize here. Now this term should be reminiscent of something. VAEs. The reconstruction term, right? Because if you remember, this seems very similar to we had this expectation Q of Z given X log of P theta of X given Z.
Right.
The decoder, right? You sample Z from the encoder parameters, you pass that into the decoder, you get X. That's what we were trying to do. Similarly here, this is X naught, our data. This is the latent that we are trying to use to get the data, right? Very simple thought process. But this expectation is over a very large quantity. So any thoughts how to reduce this? Do you think all of those variables are important? Let me call this as term 1 and term 2. So term 1, if I were to, expand, what will happen? Mm-hmm.
X1 given X all the XT,
Mm-hmm.
like X2X,
To capital T, okay. So think about it. Basically, here, what is this a function of? The term inside the expectation is a function of what variables?
X0 and X1.
X0 and X1, right? Okay. Expectation is over. Yeah.
So
Okay.
it's essentially it's not an X0.
X1 and X1 will only affect this, right? Okay. Intuition, right? Mathematically, how will we show it? Like what you have to do to say that, okay.
Like, Q X1 to T
Uh-huh.
given X0 can be decomposed as
Uh-huh.
many like multiplications product of.
Right.
We only take those particular terms which involves X0 and X1.
When you say will take only because remaining will just get integrated out.
Right. Correct.
Right? Because all of those will become distributions, and again, integration over all those distributions will just become one, right? That's one way of going about it. Another way could be looking at conditional expectations, right? So basically, we can write something like this, right? So let's say expectation of X over some random variable can be seen as expectation over X, expectation over, sorry, Y, and let's say Y given X or X given Y. X given Y, correct. Right?
Correct.
Conditional expectation, right? So what we're doing is we look at the joint distribution of P, X and Y, and then we separate that out as a marginal over Y and then conditional over Y, right? This is exactly the point. So what we can do here, this can now be decomposed as expectation over, yeah, so expectation over Q of X,
Not X0.
X naught will always be conditional because here also is always conditioning, right?
Okay. I was just like comparing X and Y there.
Right. So here I have X1 to T given X naught. So that can write here. So what I will do is I will write this as X2 to T, let's say.
Okay.
Again, given X naught because I cannot lose that. So now I write the expectation over X1 given X naught. Sorry, given X, yeah, sorry, correct, you're right. Given X2 to T, right? X naught and X2 to T. Right? This function, this log P, this, for now I'll just keep it like this, right? Is this clear? Right? So I'm just writing X as Y and X given Y. So this is the X part. This is the Y given X part. Sorry, X given Y part, right?
So first one is Y.
Sorry?
First one is what?
X2 to T.
is Y.
X2 to T is Y. Okay.
And X0 is kind of X.
Because it's conditional initially, it'll remain conditional everywhere. So I mean, yeah, right? This clear?
Right.
Now this can now be seen as expectation of X2 to T given X naught. Now we know that this is just q of x naught, x1 comma x naught, x1 given x naught, right? Because that's a Markov chain, right? So this can be written as q of x1 given x naught. This is the leap we are taking, the Markov chain coming up here, right? So log p. Now, the point is this as a function doesn't depend on 2 to t, x to t random variables, right? So this can be taken out of the expectation, and therefore this just becomes x1 to x1 given x naught log p theta of x1, sorry, x naught given x1, right? Then expectation of 1. That's just 1 into 1. Is this clear?
So, approximate. So neural network is approximating the backward process, right?
Yes.
So it's going from t to t minus 1.
Correct.
Q is going from x0 to x1.
Yes. So Q is always going forward process. That is data to noise. Neural network is trying to go from noise to data. P theta. That's the neural network part here. Right? I mean, yeah, so all everywhere here is p theta and all. I mean, just yeah, that's yeah. All this become p theta and all of this. Yeah. Okay. Clear until now? This step, okay. Huh.
So Markov chain version is on
Huh.
x1.
Right. So if I give the previous variable in a Markov chain, it is independent of any other variable. Right? If I give, hence because I have x naught here, none of these variables will affect the x1 anymore because x naught is present in the conditioning. So therefore, this distribution is equal to this distribution.
And this is like the encoder with x1 as the
Encoder or decoder?
This one. Oh,
this term.
Decoder.
Yeah. Right?
And the previous term was?
Which previous term?
So you are discussing the same thing, no? Here. So x naught from x1.
So x naught to x.
So this is basically this is a decoder.
Decoder.
That's the encoder, correct. X naught to x1 is encoder.
X1
data to
x0.
x1 to x0 is decoder, correct.
So P of x1 and x0.
That is correct. This is the decoder part.
This is a decoder. Yeah.
That is correct. Now what was q of x1 to x1 given x naught? The final where it came was this one, right?
Q is also a neural.
Is it? Interesting. This is a good discussion. Yeah, but is it a neural network here in our case?
No. That's right. Distribution we know.
We know our distribution, right? That's the biggest difference between this VAE and this one.
So how do you know the distribution?
The equation x equal to
oh, in that way.
Right. So because I can always
know the distribution of px naught.
We don't know the distribution of px naught. We don't need also, by the way, because I just want the conditional on x naught. I don't need x naught at all, right? Hence we came to this. We said xt given x minus 1 is what? That's what we wanted to look at. And throughout the whole discussion also, we never came to q of x naught anywhere. It was always the point of, okay, what is the whole distribution x1 to t given x naught, right? Which we know, right? And it's also how the variational this one was done in the VAE formulation also. In VAE formulation also, when we took the variational distribution, we said q of z given x. That is my variational distribution, not q of z, not q of x, nothing. That's the point. Okay, very similar to VAs. Okay, fine. Okay, so this is the first term, clear, done and dusted. Now let's look at second term. Second term, again the point is summation t equal to 1 to t minus 1. So what we'll do is we'll just look at this expectation, try to figure out what this comes out to. So let's look at that. Second term, we'll look at this expectation of x1 to t given x naught. Log of p of xt given xt plus 1 divided by q of xt given xt minus 1. Right? This, we have this expectation. Now, similar sort of thought process can be applied here. What would this intuitively turn out to be? What would this expectation turn out to be? Again, the question here is basically, do I need all the variables or not?
You only need those xt and xt plus 1.
And
It's not.
And xt plus 1 and xt minus 1 also, right? So similar sort of thought process can be done here. Let's look at that. So basically what will end up happening is you will write this as q of x t given x t minus 1. Yeah, I forget the form. Xt minus 1, or connect it like this actually. So x t minus 1 comma xt plus 1, okay, given x naught. Then expectation of what remains is let's say x1 to t minus 2, comma t plus 2 to t, capital T, given, right, x naught, comma xt minus 1 xt plus 1, and all of this stuff here, right? So now what will end up happening is we will say similar sort of things, right? So now here t plus 2 to capital T, right? Now t plus 2 given xt plus 1, that will go away, right? Then until t it will go away. Then what will happen is we'll now make an argument saying that okay, these all variables don't depend on 1 to t minus 2 at all. I can take it out. Expectation of that of 1 will become again 1. So finally this will turn out to be just this expectation, right? So q of xt minus 1 xt plus 1 given x naught log p of xt given xt plus 1 q of xt given xt minus 1, right? Now we'll do some more math jugglery. What we will write this as now as xt given xt minus 1, okay? So we'll now write this as q of xt given xt minus 1, okay, log p of xt plus 1 divided by q of xt minus 1, right? What remains is this expectation, which is q of x naught term has to be here, and again xt minus 1 is here, so that's enough for xt, not a problem. And what remains is basically xt plus 1 and probably xt also. This will turn out to be same thought process. Xt given xt minus 1 xt plus 1 x naught, right? And then this could then be written as q of, so a given b, and then xt minus 1 xt plus 1, yeah, given x naught. So if you see, this is this is what it turns out to be, right? So yeah, so a given a into b given a, yeah, right. So you'll get a b, yeah, correct. Okay, this is xt minus 1 comma xt plus 1 given x naught, right? Okay, so this, okay, now this should be reminiscent of something. What is it reminding you of? Again, recall VAs. Everything is very close to VAs because we have again assumed a variational distribution now. DKL term, which is DKL Q. But Q of what? You'll have to give because Q is a xt plus 1, right? Minus of that, right? Minus of that, or no?
Plus.
plus, minus. दो ही option है. Think of again VAs, go back to VAs always, right? So there also what we had expectation of whatever, then we are minus KL of Q with P and all of that, right? So again, let's recall KL formulation and KL formula. PQ is basically log, so P by Q, right? In expectation over P, right? So this P has to be the distribution for sampling and also the numerator. That's how I remember always, right? So negative of that because log will become negative, right? Now this is the internal term. This is an expectation over this KL, right? So expectation of Qt x minus 1 Qt xt plus 1 given x naught of this quantity, or I can just write it as like this, right? So this is what we have come down to. So now therefore this the elbow that we had is basically nothing but expectation over Q of x1 given x naught, right? This is your encoder sort of a formulation. Decoder comes here, x naught given x1, and we had the term which tried to match your posterior, to the prior, right? So so that was basically this expectation over Q of xt minus 1, xt plus 1 given x naught, then KL of this quantity, right? P of xt given xt plus 1. Again, see, this is the idea here is both these distributions are over xt. So KL is defined. That's just keep in mind always, right? So, but the conditional is different. Here we're conditioning on the previous step. Here we're conditioning on the future step, right? Okay, fine. So how would we operationalize this one? Let's say this is what the elbow is, and we'll see another formulation. But for this particular scenario, how will we operationalize it? How would you go about implementing it, for example, let's say, right? Expectations are there. We know what to do with expectations. So how would you then, let's say, bring it down to a place where I have samples from X naught? How do I do that? So first term should be straightforward, right? Second term, how would we, go about computing if I have only samples from X naught? Second term. First term is simple. That okay? Do we agree the first term is simple? Oh, okay. No, we don't know. Okay, fine. That's a good.
Expectation is simple.
Yeah.
Because there's only we have to sample using that. That's a Gaussian distribution with that.
The mean.
Alpha t whatever.
Alpha t mean and variance. We know that. Closed form. Yeah. No issues with reparameters and nothing. All that not required here. Simple, right? So what I could do here for this first term could basically be, again, we'll use a multi-color estimate, right? We can't compute all this in closed form. So what we will do is we will say this first term should be equal to 1 by n, right? I have n samples. Let's say n equal to 1 to capital N, right? I will look at log p theta of, let's say, x naught n, nth sample given x1n, right? Where x1n will be a sample from the Gaussian distribution, which is okay centered around x1 whatever, on x1, but centered around the mean alpha 1 x naught, which I already have, right? Nth sample, same thing, comma 1 minus root of 1 minus alpha naught I, right? So I have x naught n, that is nth sample. I have the mean, I have the variance. Take a sample from that mean and variance, pass it through the decoder. That is basically taking my x1 to x naught, right? Pass it to the decoder. That gives me my log p theta. Simple, straightforward, right? And there's no issue of reparameterization or anything. We don't need any parameters to backtrack, nothing. You can just do a simple Gaussian sampling and move ahead, right? Fine, that is done. Now, second step, how do we do? Second term. In similar spirit, how do we go for the
So
second
Q
term?
xt given xt minus 1 we know.
Correct. Yes. Yes, we know.
And P of xt given xt plus 1 also we know.
Right. Why is that? Neural network.
Neural network.
Right. Okay. Then, okay, next step.
That is P theta only.
P theta, sorry, yeah, that's all P theta. Yeah, P theta.
So okay, that we know. What's the problem?
So
Close form solution.
give me a sampling procedure. Give me how will I run this? How will I update theta? At the end, I want theta, right? I have to update theta from here, right? I have to maximize this. So how do I give me terms in terms of theta? We can't do Monte Carlo, is it? Okay.
Because there are two terms. It will be expense.
We'll come there, but without that, okay. How would you go about doing it? It's expensive, fine, but how would you go about implementing it?
Take the random sample like 0, like from the data.
From the data, okay.
Use it to generate xt minus 1. No.
Okay.
Yeah, so generate x1, x2, x, and so on.
xt t minus 1.
And xt plus 1. All those things. Use that values xt minus 1 and xt. This is a dot. What is it? Sorry, I missed that. There's only two terms here.
Which one?
This q of xt minus 1, xt plus 1.
This one?
Only two terms, huh?
Only these will remain, no?
Okay.
And let me just verify.
Just use.
Yeah. Go ahead.
Use this.
This correct. Yeah. Okay. Use.
Those
Sorry.
samples,
Compute the DKL.
How do you compute the DKL?
Yeah, that expectation of.
Expectation of.
Like that formula.
Which formula?
DKL formula.
So Q is now basically we can compute closed form, I think, for this.
Why? Because both are
Probably.
Gaussian.
Gaussians. Probabilities. Right. Both are Gaussians. Right. So we have the formula as you were saying. Like DKL closed form solution exists for two Gaussians. So I can get the closed form solution for this. Now, but the point is, I will run that closed form solution. I will evaluate the closed form solution by getting this x naught, right? So I have x naught, and I need not go all t steps, by the way. Why? Xt minus 1 I can get, right? Xt minus 1 I can get immediately from x naught.
By putting the
appropriate time, just put t minus 1, I will get xt minus 1 given x naught. That I can do. I can get xt also from x naught. I can get xt plus 1 also from x naught. Right? Just take one x naught, get xt minus 1, get xt plus 1, get xt, and run this care.
Should not be given, right?
They are independent. No, we're not talking about xt minus 1 and xt plus 1 being independent.
So if we use different epsilon, it will be independent.
You're saying, sorry, okay, tell me what is independent, xt minus 1 and xt plus 1, is it? No, but how will that be?
It can't be given.
So because see,
x0, sample xt, generate xt minus 1 from x naught.
From x naught.
That equation is root of alpha.
Right.
Yeah, sorry. Sample.
Correct. Sample, okay. So this can be sampled as Gaussian. Given x naught, right? Sampled as?
And that, yeah, t minus
1 minus alpha t minus 1, sorry, not 1 minus here. Alpha t minus 1 bar until alpha t, right? X naught, comma, 1 minus alpha t minus 1 bar I. Okay, fine.
So, yeah, and then again xt plus 1.
Xt plus 1, given x naught.
That same thing. We can.
Right.
Okay. If we use different, basically, this generating process are not, if not combined, then xt minus 1 and xt plus 1 will be.
Independent.
It would be.
You're saying the conditional variables are independent, is it? Condition on X not, they are independent. Is that what you're saying? That's what I have to think about.
Which might be true actually.
I was thinking that about that also. If I condition it, then.
So I'll put it in the way. Xt plus 1 given xt and xt minus 1 given xt minus 2 are surely independent.
Correct.
I think if we do the maths, these two also will
should be independent. Okay. But I'll just check this and come back. Yeah. So xt minus 1 given x naught, is this independent of xt plus 1 given x naught? Right? That's the question that we're trying to do. Yeah, with this generating process, right? That's the thing. Okay. Okay. Fine. Yeah. So okay. So we have a way to operationalize this whole procedure also, right? I have x naught, take a sample, get xt minus 1, xt plus 1, xt, evaluate the scale. I can evaluate that. The scale will come down to basically having some parameters theta, right? Because mean usme aayega, so it will have the parameters theta. I can use that to update the equation, right? Now, as Yash pointed out, this generating twice all of the thrice actually speaking, you will generate xt also, you generate xt minus 1 also, you generate xt plus 1 also, right? All of these values you're trying to generate. This is going to be a high variance system, right?
We are running the neural network 3 times.
The sampling itself is a high variance system. Now see, okay, but I mean the point is this expectation you're trying to approximate by a Monte Carlo estimate.
Right.
That estimate will be a high variance estimate for this particular expectation. That's a problem.
Correct.
We need a lot of samples to be able to do a good estimate. Now this is exactly what the authors also mentioned, and now they're trying to look for some, can we do something about this, right? So for that we'll go into the next part of this one. So here we are now looking at okay, so we have xt given xt minus 1. This we know is Gaussian, right? Okay. We also have xt given x naught as Gaussian.
Yes.
Okay. I also have xt minus 1 given x naught as Gaussian, right? These are all Gaussians. Fine. Now, can I write q of xt given x naught equal to q of xt given sorry, not this. Can I write xt minus 1 as xt minus 1 comma x naught?
Yeah.
Right? Markov chain, right? If a condition on xt minus 1, anything else is independent. So this remains same, right? Now, can I use Bayesian Bayes theorem on this? Right? So I have P of A given B. I can write it as P of B given A, P of A, P of B. Right? Now, if I had to do that, what would this turn out to be? Can you write the terms?
Q of xt.
Q of xt is where? Here.
Here, given.
No. Right. Xt minus 1 given xt comma x naught, right, into q of a, that is again xt minus 1 given x naught, right, divided by q of xt given x naught. Is this fine? Right? Which one? Oh, sorry. Yeah, correct. This will be xt and this will be xt minus 1, right? Correct? Is this fine? So now we use this equation so we'll use this in our derivation what we did previously. Okay, so let's go back to the drawing board. So log again same p theta of x naught. This is greater than or equal to, we know the expectation, right, of q of x1 to t x naught, right, into log of p theta x naught to t q of x1 to t given x naught. Right, this as usual, which we came to this problem. Now we'll look at this term. This is equal to expectation log same p theta, so p of x t, p probability multiple this one, p theta of x t given xt minus 1 c plus 1, right, into same thing here. So we'll do t equal to 1 to capital T q of x t given xt minus 1, right. Now this can again be written as same expectation over log p of xt. Same we will apply q of xt given xt minus 1 here, right. That's one term. Second, so this becomes yeah, so pi of t equal to 2 to capital T, same, right. Now this term I can write it as again same, we'll take out p theta of x 1 given x naught outside, t equal to 2 to capital T again, right. Is this right? Oh, this becomes 1 to t minus 1, right. Q capital T is going away, right. And then I have p theta of same xt given xt minus 1, right. T equal to this is t plus 1 and t, right. What was this? x t sorry, xt minus 1 to t, is it? Right. No. So I need t minus 1 here and t here, right? Correct. This makes sense, right? Or no?
No. It's still forward process.
Sorry. So t minus 1 to t minus 1.
Yeah.
Right? Correct. Backward, right? T to t minus 1. And this becomes, yeah, this is fine. And then x1 given x naught goes here. Yeah. Okay, fine. So this is what we come to at the end. Xt minus 1 to xt. Okay, this is fine. Now we'll look at, so this again becomes same, p of xt, q of xt given xt minus 1 here. Same p theta of x1 given x naught, right. Now here what we'll do is we'll look at this particular term like this, right. So we'll say this becomes, okay, so this becomes t p theta of xt minus 1 given xt. Now we'll replace this idea, right. So q of xt given xt minus 1 is equal to this, right. So this becomes q of xt given xt minus 1 comma x naught, right. And we always have access to x naught because we are looking at p of x naught, right. So this is always there with us. T equal to 1 to t minus 1. Now we'll leave for this all of these terms for now. Let's look at this term. So p theta of xt minus 1 given xt, right. Then will also remove this term, that is q of x not given x1 from this. Sorry, x1 given x naught.
X1 given x naught.
Right, x1 given x1 I'll remove from this term. So I'll have from t equal to t to capital T.
Right.
Is this correct? Which index?
No, index should be changed. So either like limit or see, we took one term out. So only the lower limit will change, upper limit will remain same. I think so.
Oh, sorry, correct. 1 second. Yeah. No, 1 second. This is wrong on my side. So this is, for example, just let's not take that term outside. Rather, now this is fine, right?
This completely.
So this is still T to 1 to T. This is fine. For process, T minus 1 to capital T, and the last term will be Q1 x1 given x0. Exactly what we want, and I'll remove the first term. That is for T equal to 1 term I'll remove. So I'll have T equal to capital T 2 to capital T. Same thing here, right? So I can now write this as a product of ratios. So now we'll look at this term. So Q of xt given xt minus 1 comma x0, right? Okay. Now this second write it as p theta xt minus 1 given x0. Same jugglery we'll do here, and we'll write this as this term q of xt minus 1 given xt comma x0, right, into q of xt given x0, right, and then this becomes a numerator q of xt minus 1 given x0. Is it fine? This is clear, right? So now what we'll do is we can now look at this product. This is this term, fine. Now the product, if I were to look at this, p theta of xt minus 1 given x0, this t minus 1, no? Xt comma x0 into this product, right? The second, right? Is this fine? Yeah. What will happen to this product? We can cancel a lot of terms actually, right? So what will remain at the end? Sorry?
So qxt given x0.
Okay.
Okay.
So let's say for 2, if I were to expand this, what will happen given x0? T equal to 3, if I expand, I get q of x2 given x0 into q of x3 given x0.
Yeah, x1 by xt basically.
X1 by xt, right? So what? So I'll get q of xt x capital T minus 1 given x0 divided by q of x capital T given x0, right? All of these get cancelled. So this will become a product of this ratio of these two terms, right? Okay, fine. This is this term. This term is what we're interested in actually. So this I can write this as 1 second. How did x not come here now? So this is basically xt. This term, right? It remains as it is. We're not messing with this term currently, right? So now this term is going to become summation under log, right? We're still there. We're still in the log space. So finally, what will happen? Let's look at that. Expectation is there, right? Log of, I have one term is p of xt, right? This I not remain anymore, right? So p of xt into, then I have p theta of x1 given x0 I removed in the first step. So p theta of x1 given x0, right? This term done. A product t equal to 2 to t, and I had this one still remaining. I had removed that, hence I got this term. So by q of x1 given x0, correct? Then this product turned out to be this product into this term, right? So into q of x1 given x0 divided by q of xt given x0 into product t equal to t to capital T, this p theta of xt minus 1 given xt divided by q of xt minus 1 given xt comma x naught. Is it clear? These two can get cancelled. Very simple. It turns out to be the same form. The first two terms again come back, right? So what we have p theta of, log here, log
Q was 60 minus 1 is Q is.
correct. So I can always define the conditional in the other way, right? In the Q space, in the Q Markov chain, look at the previous one, right? That's the value. So then plus expectation of log of P of xt given over Q of xt given x naught, right? These two terms, this term, this term, this term done. What remains is plus summation t equal to t to capital T expectation of log of p theta of xt minus 1 given xt divided by q of xt minus 1 given xt comma x naught. Right? Again, same decoder part came here. This has no learnable parameters. Right? P of xt is Gaussian. This is Gaussian. Nothing to learn here. Right? Right, Sanchit?
Sorry.
Correct, no?
Nothing to learn by using.
Huh. So do you have any dependence on the parameters of the neural network? Theta coming up anywhere here?
No.
No, right? Because this is fixed Gaussian and Q doesn't depend on theta at all in any way. So this is free of that. And same thing again will apply same logic back. I will get, so this again Q over the whole distribution, joint distribution, but again it will come down to x1 given x naught. Right, same thing. Now this is again where we were stuck before. Right, now if you see here, this term has only t minus 1 and t. No t plus 1 is there in this particular term, right? And that's all thanks to this particular way of writing it down, right? Because if I give conditional, it's independent of x naught, so therefore I can write it as in that way, right? So this is what it turns out to be. So now again, let's think about this. X1 to t given x naught is here, right? So we'll think about this particular term. So this term, if you see, what will end up happening is again same idea. It doesn't depend on any other terms other than t and t minus 1. So I can just again write it down again in this form. So I'll write it as expectation over q of xt minus 1 comma xt given x naught. Right? I'm still not taking that internal this one. Divided by q of xt minus 1 given xt comma x naught. Right? Now, this again I can break down into conditional expectation, right? Expectation over two quantities, right? What will be the two quantities? Any thoughts? What would you want here? So if you can you get it in the DKL term, right? So how would you, because see, that's where we're headed to, because I have two distributions over t minus 1, xt minus 1. If you can get DKL, I can hopefully try to compute that, right? So basically I want a distribution.
Basically
this distribution we want, right? So then what will remain here?
Yeah, so
xt
x given x.
Given x naught, right? Now this can be seen as expectation over q of xt given x naught minus dk, right? Q of xt minus 1 given x naught, xt comma x naught, p theta of xt minus 1 given xt. right? This is exactly where we came, but now that what all things we need to sample?
So from where did this QXT given X naught came?
This distribution, no? So this is basically expectation of, again, same thought process. Think about it. Expectation of X can be seen as expectation over, let's say, Y, expectation of X, X given Y. Right? So I have now, these two are joint distribution of two variables. So I can write, I want this X here. This is my X here with here.
Location, okay.
Yeah. Location change. Correct. XT became a conditioning variable here. Right? And that's why I could write DKL. Because the expectation and this term is exactly the same. So I can write the DKL term. Right? Okay. Now, all good until now. We lost the issue of that this one. Now how would you compute this?
Compute this DKL term.
Yes. Now it's multicolor, right?
So, so can we still use that formula for KL divergence?
Yeah.
Is this Gaussian?
This is Gaussian.
Okay.
No.
And what Gaussian is that? If it is Gaussian, can you tell me the form?
If xt given xt minus 1 is Gaussian, then xt minus 1 given xt is also Gaussian.
Always? Is that always the case?
I think so.
It would be like it did some similar formulation. No?
Correct. But that was for the forward process. Correct?
This is the process also
backward process P theta.
Oh, I see. So
right?
Okay.
What is the why it's not obvious?
Why should it be obvious? See, okay. If it is obvious, what is the mean and variance of that? Okay, let's.
No, always.
It may not be always, no. Should it be always? I don't know, but I'm asking. I also don't know.
Just watching, looking. Bishop.
Okay.
They say if conditional is Gaussian, then have to look it again. I think it's always. I thought it's always the case.
If conditional is Gaussian, the reverse condition is also Gaussian, you're saying. But if that was the case, then VAEs would have been solved, actually, right? Because so think about it. Gaussian mixture model. How do we model the Gaussian mixture model, right? We say P of, let's say, X, for example, is some, pi I into Gaussian of, Xi with some mean and variance, right? Mu I, sigma I, right? So what does this mean? So if I take Z as these values, let's say, I equal to 1 to K, if I take Z as a categorical variable, which goes from 1 to K, right? P of X given Z is Gaussian. But is P of Z given X Gaussian? No.
It's definitely not actually.
It's definitely not, right? Okay. So we have established that it is not trivial. Fine. Okay. So what all information do we have? We have information that xt given.
Continuous variable, what's the case?
So we'll have to think. So you're saying that okay, because you're saying this is some continuous variable.
So then it should be integral here then, not summation.
Integral, correct. No, but okay, so this is exactly VAE formulation, no? So think about it. So what do we do in VAE formulation? P of X equal to integral P of Z into P of X given Z. Correct? This is exactly what we do in this one. If this was the case, right? If P of Z given X was Gaussian, right? Then I have the true posterior with me. There is no variational inference. There is no VAE existence. Okay.
Yeah.
Correct? Okay. So,
Px is unknown. That's why we are not able to get.
But P of X given Z, we assume no, it to be Gaussian and move ahead. For example, in normal.
Q, proximities. Question.
I'm talking about the decoder. Decoder also we assume Gaussian. That's why we get MSE loss.
Yeah, no. So here
Huh.
Px is unknown.
Px is unknown, correct.
That's why Pz given x we cannot say is Gaussian. Otherwise,
Okay.
so if Px given z is Gaussian and Px is Gaussian,
And Px is Gaussian, okay. Huh.
then Pz given x is a Gaussian.
Okay. But how does it apply here? Because Q of xt is not Gaussian, right? Q of xt is not Gaussian. That much is very clear.
That is correct, right? What I said this time.
I'll have to think about it.
Px is Gaussian. X is Gaussian.
I understood.
X given z is Gaussian.
If x is Gaussian, x given z is Gaussian,
Then
z given x is Gaussian, you're saying.
yeah,
Okay.
obvious.
Let me check this.
Yeah.
I mean, I'll have to think. Okay, fine. So, but here the rule, let's say it doesn't apply because Q of xt is not Gaussian. That much we know. Q of xt is not Gaussian, right? Q of xt t tending to infinity is Gaussian. That we know. But we are talking about finite t, right? Okay. Okay, but what all other information do we have? We have, so one thing that we have is t minus 1, so xt given xt minus 1 is Gaussian, that we know. What else information do we have? Which can hopefully help us understand where to go with this. Is all of this, right? This is Gaussian, this Gaussian, this Gaussian. Now the issue where it comes is this Gaussian? This is what we're trying to ask. Correct? So now let's bring that back here.
It is okay. Yeah, we don't know.
Yeah. So Q of xt minus 1 given xt comma x naught can be written as Q of.
Useless there.
Here it's not useless, see.
Oh, right, not here.
Not here. That's the point. Here is not useless, right? Now this is equal to Q of xt given xt minus 1 into Q of xt minus 1 given x naught divided by Q of xt given x naught. So this is correct. Yeah, t minus 1, t is down. Yeah, okay. So now, okay, if I write it like this, now does it help to see if it is Gaussian or not? This is Gaussian, this is Gaussian, this is Gaussian. Everything is Gaussian here, right? It'll turn out to be Gaussian, right? Why? In intuition, if you think about it. Simple thought process. So this basically Q of xt given exactly exponential term, right? Proportional to some exponential, again proportional to exponential, again proportional to exponential. Some Gaussian only will come out.
Maybe he was right.
But in this process, see his point was this in general. This doesn't apply to our use case because of the fact that Q of xt is not Gaussian. It is becoming all of this because of this particular thing.
I see.
Given x naught, they become Gaussians. At the end, this is also Gaussian. So all of this turns out to be a Gaussian. Now what remains is mean and variance. What does the mean? What is the variance? Because we know the mean and all of these and everything.
Basically, we know all this.
We know all of these, exactly. We know all of these things. So we can find a closed form solution for the mean and the variance, and we will do that next class. Okay. So at the end, what will turn out to be? This will turn out to be Gaussian, and then we'll look at how this can be operationalized. What's the closed form and then implementation. Yeah, clear? Okay. Let's close the class.